NASA's biggest alien secret exposed. He's holding a glinting bead between tweezers when someone off camera says, "That's just cosmic junk." Avi Loeb doesn't flinch. The spherule looks ordinary, iron, nickel, a pinhead of metal pulled from the Pacific. But its story isn't ordinary. One object, Oumuamua, slipped through our solar system and accelerated without a visible engine. Another, IM-1, hit our atmosphere faster and tougher than it should. Are these fragments of interstellar technology, or just misunderstood rocks? If Loeb's right, it's the first physical evidence of alien craft. What if the first artifact isn't a saucer, it's a speck? What does he know that NASA won't say, and why has the quiet been so loud? The night the sky threw a rock back. It started with a flash over the western Pacific on January 8, 2014. The U.S. Department of Defense watched it the way they watch everything bright and fast. Infrared sensors registered a fireball slicing into the atmosphere at a speed that didn't fit the usual charts. In the public NASA CNEOS catalog, the event later appeared as a small meteor with a strange label, hyperbolic pre-atmospheric velocity, faster than the sun's gravity could reel back. Most meteors are bound visitors. This one, if the numbers held, came from interstellar space. There was a catch. The numbers were blurrier than the community liked. The crucial error bars on velocity were classified, hidden inside systems built for missile warning, not for peer-reviewed science. You could see the dot on the plot, but not the shadow that told you how sure the dot really was. For years, that uncertainty kept the event, cataloged as CNEOS 2014-0108, stuck in a strange limbo. Interesting, tempting, not publishable without a fight. Avi Loeb saw the dot and couldn't stop thinking about it. By 2019, he and his student Amir Surej had dug through the catalog and flagged the outlier. The path traced back on a hyperbolic track. The speed before atmospheric drag still looked too high to be from our solar family. If that was true, IM-1 wasn't just a meteor. It was a messenger from another star, the first interstellar object to hit Earth we'd ever recorded. But the journal reviewers wanted those error bars. Without them, the claim stalled. For Loeb, this was déjà vu. 2 years earlier, Oumuamua had torn through our system and made careful scientists uncomfortable. He'd watched the debate turn rigid when the data stayed weird. Now he faced the same problem in a different disguise. Military sensors with answers locked behind classification. Open science runs on transparency. Defense systems run on secrecy. How do you build consensus when the evidence sits behind a badge? Then in April 2022, something unusual happened. The U.S. Space Command sent a letter signed by a senior scientist stating, with high confidence, 999%, that the meteor's pre-atmospheric speed was indeed high enough to be interstellar. The key uncertainty numbers had been reviewed within the classified system. The physics checked out. In one paragraph, the event jumped from rumor to recognized outlier. It didn't settle every question, but it moved the goalposts. The first known interstellar meteor had hit Earth. That validation came with a new set of stakes. If IM-1 was interstellar, what was it made of? The light curve from the 2D sensors suggested it didn't fragment the way typical meteors do. It held together deeper into the atmosphere, hinting at unusual strength. Was that a quirk of entry angle and size, or a sign of material we didn't usually see? Without fragments in hand, nobody could say. The speed and trajectory were one kind of extraordinary. Composition would be another. Loeb didn't want to wait for another memo. He moved. He started mapping the fireball's final seconds, cross-referencing wind patterns, ocean currents, and drift models to estimate where debris, microscopic and macroscopic, might settle on the seafloor north of Papua New Guinea. He gave the object a name, IM-1, and a target, a fall ellipse, a narrow swath of ocean where spherules, tiny melted droplets, could have rained down, cooled, and sunk. There were obvious criticisms. The CNEOS data, even with the classified review, wasn't collected for geology. Sensor calibration remained opaque. The ocean is full of industrial residue, ship emissions, steel slag, paint, even cosmic dust from countless ordinary meteors. Searching a deep, windy patch of ocean for particles smaller than a peppercorn sounded like a needle-in-haystack story without the haystack map. But the potential payoff changed the calculus. If you could bring up metal that chemically and isotopically matched an interstellar origin and showed unusual strength, you might pull the debate into a lab where opinions matter less than spectra. Loeb framed it plainly. If the numbers say interstellar, then the ocean floor is an archive, and archives can be read. He raised funds, assembled a small team under the Galileo Project banner, and contracted a ship with a simple plan: drag a magnetic sled over the mapped corridor, sieve the collected sediment, and separate out spherules for analysis. It wasn't elegant, but it was testable. Either you find a concentration spike in that line compared to control transects, or you don't. Meanwhile, in the background, caution hummed. The scientific community knows how easy it is to jump at a shiny anomaly. The 1996 Martian meteorite with supposed microfossils, the Viking life experiment ambiguity, decades of UFO claims, each left bruises. The pushback came in careful language. Confidence in origin isn't the same as confidence in composition. Without a clean chain of custody and rigorous contamination controls, any positive finding could evaporate on contact with peer review. And the critics had a point. Extraordinary claims don't just demand extraordinary evidence. They demand ordinary procedures executed flawlessly. But the clock was ticking. Currents shift, sediments move, and attention wanders. Loeb argued that the search itself could be iterative: collect, analyze, publish methods, invite replication. If the first pass found nothing, that was an answer. If it found something, the real work would begin. What he couldn't accept was paralysis. An interstellar meteor had happened over water shallow enough to reach. Doing nothing felt like turning your back on a once-in-a-generation chance. To understand why he moved that fast, and why his framing split rooms, we need to go back 5 years earlier, to an object that acted like it had a mind of its own. Oumuamua, the thing that didn't behave. In October 2017, a telescope in Hawaii flagged a moving speck sliding against the stars. Panastarrs does this nightly, but this track had a weird curve, too fast, too sharp, the kind of arc that says this visitor wasn't bound to the sun. Astronomers ran the orbit and blinked. It came from outside the solar system on a hyperbolic path. They called it 1I/Oumuamua, Scout in Hawaiian, and immediately it refused to act like anything in the category list. Comets usually announce themselves with drama, gas jets, a glowing coma, dust tails that bloom as sunlight cooks ices. Oumuamua gave nothing obvious. No fuzzy halo, no tail, just a faint tumbling point whose brightness rose and fell in a pattern that hinted at an odd shape. The light curve stretched by a factor of roughly 10, suggesting something elongated or very flat. People argued a cigar, others argued a pancake. Both were guesses standing on flickers of light. Then came the twist that pushed it from interesting to unsettling. As it left the inner solar system, its trajectory changed in a way gravity alone couldn't explain. The acceleration was small but real, measurable across multiple observations. Comets do this when outgassing acts like a thruster, but if gas was pushing, where was the gas? The Spitzer Space Telescope looked for warm dust and typical volatiles like CO and CO2. ALMA checked for radio signatures. The detections didn't show the usual suspects. Oumuamua kept moving as if something was nudging it, and nobody could point to a visible engine. Here's where Loeb stepped onto the stage. If there's no coma and the push is real, he argued, then one simple explanation is sunlight itself. Not magical sunlight, radiation pressure, the steady push of photons. For radiation pressure to matter, the object must have a high area-to-mass ratio, like a thin sheet catching wind. A natural rock with that geometry is hard to conjure. A manufactured light sail is easier to picture. He wrote it plainly. Oumuamua could be artificial. The mainstream recoiled, not because it's impossible, but because it's a leap. Astrophysics tries natural first and exhausts the inventory. So the community started inventing natural shapes and materials that could mimic a sail. One proposal imagined a hydrogen iceberg, a frozen puff that sublimates invisibly, providing thrust without leaving a detectable trail. Another argued for a nitrogen shard, chipped from a Pluto-like world, its ices venting quietly. Others proposed a fractal, extremely porous dust aggregate, featherweight but voluminous, pushed by light like dandelion fluff. Each idea solved a piece and broke somewhere else. Hydrogen ice doesn't survive long in interstellar space. Cosmic rays heat and erode it over millions of years. Nitrogen shards might form, but you need to explain how you produce enough of them and keep them intact. A fluffy fractal could be pushed by light, but could it survive close passes to the sun without disintegrating? Meanwhile, the non-detections of carbon-bearing volatiles forced tweaks to models. Maybe CO2 was locked up, maybe outgassing was directional, maybe dust grains were larger than expected and stayed invisible. Maybe did a lot of work. Loeb leaned into the discomfort. He wasn't claiming proof. He was saying the data made technology a live hypothesis that deserved a seat at the table. But culture matters. The field had scars from past claims that ran ahead of evidence. So reviewers kept asking for one more natural pathway before letting light sail sit near the front. The debate hardened along familiar lines. If you open the door to artificial, you need extraordinary evidence. If you keep the door shut, you risk ignoring a clue because it feels taboo. The human moments in those months were small and telling. Graduate students whispered about applying to work on Oumuamua, but worried their advisors would steer them to safer topics. Telescope time got parceled to projects that could promise conventional returns. The public, though, devoured the mystery. Every press briefing had to balance, "We don't know," with "We're not saying aliens," a sentence that convinces no one and angers both sides. Meanwhile, the clock kept running. Oumuamua was faint and fading. No mission could catch it on short notice. We had a once-only glimpse and a mountain of inferences built from a handful of photometric points and follow-up observations. That scarcity is what made Loeb impatient. If you can't go to it, find the next one or find something it left behind. Which is why, when that 2014 Fireball's data got a second look years later, Loeb felt a pattern forming. Two interstellar signals, both misfitting their boxes. What nobody knew at the time was how sticky the Oumuamua arguments would be. Papers would keep arriving, reanalyzing thermal properties, pushing updated sublimation models, and revisiting non-gravitational acceleration with new assumptions about outgassing efficiencies. Loeb would rebut, sometimes sharply, pointing out where parameters were tuned to get the desired result. The core tension stayed. Either a natural object with rare properties, or an engineered object with ordinary physics masquerading as rarity. Two anomalies don't answer intent, but two anomalies change your search strategy. Loeb started saying it out loud. You can debate models forever, or you can go get evidence you can hold. He chose the latter, because if Oumuamua whispered a question with its silent push, maybe the ocean floor held a reply. The Pentagon letter that changed the odds. 3 years after Loeb and Suraj flagged the outlier and hit the wall of classification, an email thread turned into a lifeline. In April 2022, the U.S. Space Command released a short letter on official letterhead, signed by Lt. Gen. John E. Shaw and coordinated with Space Force scientists. It referenced the January 2014 fireball and used a phrase the community hadn't seen before in this context: 99.999% confidence that the object's pre-atmospheric velocity was high enough to be interstellar. That number wasn't plucked from enthusiasm. It came from an internal review of the classified error bars, the same uncertainties journals had asked to see. The subtext landed hard. The DoD had rerun the astrometric solution with access to the raw sensor characteristics, the calibration tables, the timing accuracy, everything that turns a flash into physics. The letter, later accompanied by a note from the chief scientist of space operations, said the uncertainties were small enough to preserve the hyperbolic solution. In plain English, the speed wasn't a rounding error. The object really arrived from beyond the sun's grasp. Legitimacy arrived with an asterisk. Scientists want data, not assurances. A confident statement is a bridge, but it's not the road. Without the underlying measurements, peer reviewers can't replicate the exact fit, test alternative noise models, or probe systematics. Some welcomed the letter as the necessary stamp to treat IM-1 as interstellar. Others saw it as authority substituting for transparency. Both reactions were reasonable. The sensors weren't built for public science, and declassifying their guts carries national security baggage. That tension, reliability nested inside secrecy, became the new battleground. Loeb treated the letter like a starting gun. He wrote that the interstellar designation crossed the threshold for action. If origin is settled to that confidence, composition becomes the urgent question. He sketched the expedition in memos and blog posts, moving from idea to procurement. The Galileo Project, his research effort built to study unusual aerial and astronomical phenomena with open methods, would organize the search. He began calling the meteor IM-1, Interstellar Meteor 1, framing it as the first of a class to be studied rather than a one-off curiosity. Inside departments, eyebrows rose. Confidence isn't composition. Confirming an interstellar speed doesn't tell you if you're chasing stainless steel, a rare cosmic alloy, or just a tough natural rock that took a lucky path. Critics pointed to the lack of peer-reviewed numbers on luminous efficiency and fragmentation modeling for this event. If you infer strength from a light curve, you're assuming how brightness maps to kinetic energy release, and those assumptions can mislead if the object was small, entered at a shallow angle, or fragmented outside the instrument's sensitivity. The reply from Loeb's side was pragmatic. Uncertainty is exactly why you go get samples and test them. He argued that oceanic micrometeor spherules are a known class of byproduct, tiny beads formed when an incoming object melts and splashes in the atmosphere, then cools and sinks. If IM-1 shed a hail of droplets along its final track, the seafloor directly downrange should hold a statistically higher concentration than background. That's a testable prediction. Map the fall ellipse using wind shear and current drift models, drag a magnetic sled along transects, and compare yields with control lines outside the corridor. If there's a spike, proceed to lab. If there isn't, publish the null. Meanwhile, the peer review problem didn't evaporate. Journals want pre-registered methods, contamination controls, and chain of custody documentation that can withstand hostile reading. Loeb's team began drafting protocols. Stainless hardware rinsed in ultra-pure water, clean room handling, blank runs to quantify shipborne contaminants, and independent labs for elemental and isotopic work. He courted funders willing to tolerate reputational risk and reminded them of the asymmetry. A small expedition could, in principle, produce the first physical material from an interstellar object ever found on Earth. The Pentagon letter also changed the field's conversation about precedent. Until then, the only certified interstellar visitor was Oumuamua, seen and lost to distance. Now, a second interstellar object was on the books, this one with an impact location within reach of a ship. That combination, confidence plus accessibility, was rare. It nudged cautious scientists to say, at minimum, this warrants a look. Pushback hardened in parallel. Some meteor experts warned that 2D-like curves are not designed to constrain strength with the precision being implied. Others emphasized how many sources can produce metallic spherules, industrial fly ash, ship paint, slag, and how easy it is to overinterpret a handful of unusual beads. The sensible path looked slow. Wait for declassification. Wait for corroborating civilian sensors. Wait for independent confirmation. Loeb chose momentum. The letter didn't end the debate. It reset the stakes. If you believe knowledge advances by confronting uncertainty with measurements, you go to sea. If you believe the risk of false positives outweighs the potential discovery, you hold position. The ship would decide which instinct got the better bet. dragging magnets across an alien trail. They sailed out of Lorengau with a map that wasn't a map so much as a probability smear, an elongated ellipse sketched from wind fields, ocean currents, and a reconstructed terminal path. North of Papua New Guinea, the Bismarck Sea looks calm from orbit. Up close it's choppy, with crosswinds that shove surface water one way while deeper currents carry silt another. Loeb stood on deck with a laminated chart, transects spaced like rungs on a ladder across the predicted fall corridor, plus control lines outside it. If IM1 shed droplets, the corridor should speak louder than the controls. The rig was simple by design. A sled frame, stainless steel to minimize stray iron, carried rows of powerful magnets wrapped in Teflon. The ship towed at a meter above the seabed to avoid gouging coral or stirring clouds of sediment that would drown the ketch. Every few kilometers, they hauled the sled aboard, peeled the magnetic sleeve, and washed the clinging grit into labeled jars with ultra-pure water. Deck hands learned a new rhythm: tow, lift, rinse, log, repeat. Each jar carried a GPS tag and timestamp, building a chain of custody that could survive a skeptical reviewer's red pen. Day one produced a discouraging truth: the ocean floor is loud with history. The magnets pulled up black grains by the spoonful, industrial fly ash from decades of combustion, break dust from ports, and micrometeoric spherules that fall globally every day. Under a hand lens, most beads looked like dull pearls in shades of gunmetal, a millimeter or less across, with smooth skins and occasional flow lines frozen as they cooled. The question wasn't whether they'd find spherules. It was whether the ellipse had more of a specific kind. A microstory unfolded at the sorting table. A technician dabbed a bead onto a sticky carbon tape, tilted it under a microscope lamp, and said, "This one's different." It gleamed less gray, more steel, harder to scratch. They started classifying by reflectivity and magnetization strength, separating the high iron, high nickel fraction from the sootier background. When they plotted counts by transect, a pattern hinted through the noise. Yields of unusually metallic spherules ticked up along the central rungs of the ellipse and fell off toward the edges and on the control lines. Not decisive, but enough to push for longer tows down the center. Back on shore, the lab work began with the basics. Scanning electron microscopy mapped textures. Some beads were featureless glassy spheres. Others had dendritic crystals, quench patterns that tell you how fast they cooled. Energy dispersive X-ray spectroscopy read the elemental mix, mostly iron, with nickel in the single-digit % range and traces of magnesium, silicon, chromium, and manganese. That by itself doesn't scream interstellar. Many cosmic spherules carry iron-nickel signatures, but a subset stood out for their hardness and the tightness of their microstructure. Fewer voids, less vesiculation, suggesting formation at high temperature and pressure. Then came the more careful assays. They ran inductively coupled plasma mass spectrometry to chase trace elements down to parts per billion. Some beads showed elevated nickel-to-iron ratios compared to typical anthropogenic slag, and a few carried unusual patterns in elements like beryllium and lanthanides. The team flagged them for isotopic analysis, the true fingerprint. Oxygen isotopes can separate terrestrial contamination from extraterrestrial spherules. Iron and nickel isotopes can hint at parent body processes. Early runs were noisy. Contamination loomed as the constant antagonist. A flake of ship paint can masquerade as a signal if you let it. Critics didn't wait. Metallurgists noted that ship exhaust and steelmaking byproducts create spherules with iron-nickel compositions all the time, some of them remarkably spherical and hard. A photo of a bead proves nothing about where it formed. Others pointed to the magnet sled itself. Any abrasion could shed microscopic particles that look exactly like what you're hunting. Loeb's team published their contamination controls. Blank tows with the sled suspended above water. Rinse water passed through filters and tested, duplicate samples processed in independent labs. They logged that the stainless hardware was low-carbon austenitic steel with known composition, and they subtracted any signature matching it. Composition told an ambiguous story. Strength told a sharper one. The spherules that ranked highest on their internal hardness scale also clustered along the predicted corridor. Under nanoindentation, some resisted deformation more than typical cosmic spherules cataloged from Antarctic snow and deep-sea sediments. That didn't prove engineering, but paired with the 2D inference that IM1 held together unusually deep, it kept the hypothesis alive. This parent body, if these beads come from it, wasn't crumbly. Meanwhile, the mapping effort paid a second dividend: abundance gradients. Along 110-kilometer transect near the ellipse's centerline, counts of the hardest, brightest spherules doubled relative to parallel lines 20 kilometers away. Loeb framed it as a likelihood ratio. If background were uniform, what are the odds of this clustering by chance? Not a slam dunk, but enough to justify a second expedition with a refined grid and a sediment core to probe below the surface layer and date layers by radionuclides. If a spike sits at the depth corresponding to 2014 deposition, the case strengthens. The human moments kept it grounded. At midnight, with the ship rolling, a grad student fumbled a vial and watched a week's work skitter toward the scupper before a deckhand snagged it with a wet glove. Someone taped a note to the lab fridge: "No coffee near the mass spec samples." On a satellite call, a reviewer said, "Publish the methods now, the interpretation later," and for once everyone agreed. The story could unfold in pieces without forcing a headline. Composition was still murky. Isotopes take time and extraordinary claims age poorly if rushed. But the field data, where the beads were, how many, how hard, hinted that they'd traced an invisible rain to a thin line on the seafloor. The shock didn't come from what the beads were made of. It came from what they might have survived. Stronger than it should be. The clue didn't start in a lab. It started in a light curve. 2D sensors don't see metal, they see energy. As IM1 tore in, the brightness time profile implied the object held together deeper than most meteors of its estimated size and speed. Typical stony meteors begin major fragmentation around 30 to 40 kilometers up. Weaker ones bloom even higher. IM1's peak energy release, reconstructed from the curve, pointed to catastrophic breakup much lower, closer to the regime where only iron meteorites and rare, tough bodies survive. Why does that matter? Strength isn't a vibe. It's a number, dynamic pressure at breakup. Roughly the air density at that altitude times the square of the velocity. For IM1 speed, that translates to tens to hundreds of megapascals if it fragmented deep, a realm well above fragile carbonaceous chondrites and into the territory of iron-nickel alloys. Loeb ran that math publicly. If the light curve's timing is right, the inferred material strength exceeds most cataloged meteor classes. Either the object was unusually small and tricked the sensors, or it was built of something tough. Meanwhile, the spherules' behavior in the tow samples quietly rhymed with that inference. The hardest beads, those that gouged instead of yielding under nanoindentation, clustered along the fall corridor. Hardness alone doesn't certify parent strength, but it sets a lower bound on what the melt droplets could represent. A parent body that, at least locally, wasn't friable dust. If the parent had been a fluffy aggregate, you'd expect easy breakup high up and a different spread of droplet types. The team kept circling the same refrain. Something about IM1 resisted. Loeb's framing, of course, leapt to the fork in the road. Manufactured alloys or rare natural phases. The engineered side imagines high toughness and high melting point materials. Iron-nickel with specific trace additives, perhaps chromium or molybdenum, microstructures tuned by controlled cooling, grains aligned to resist shear. The natural side counters with kamacite-tenite mixtures found in iron meteorites, shock-hardened phases formed in violent parent-body collisions, or quenched metal from a differentiated asteroid's core. Nature can make tough stuff. We just don't often see it at these sizes and speeds. Counterarguments followed the physics back upstream. First, size bias. If IM1 was only a few tens of centimeters, the brightness-to-energy conversion, which depends on luminous efficiency, gets uncertain. A small, fast object can mimic the light curve of a larger, tougher one, shifting the inferred breakup pressure. Second, entry geometry. A shallow angle increases the path length through thin air, smearing energy release and altering where the peak appears. Third, instrument uncertainties. 2D sensors report integrated light, not a forensic disassembly. Time resolution and spectral response matter. Adjust those knobs and strength estimates wobble. Loeb acknowledged the knobs and tried to tie them down with independent threads. He pointed to the consistency between the inferred interstellar speed, the deep breakup, and the corridor's abundance of unusually hard spherules. Each strand alone is noisy. Braided, they suggest a parent that didn't behave like a brittle rock. He also flagged the absence of typical stony meteor byproducts in the highest yield transects, fewer vesicular glassy beads, more compact metal-rich spheres. Not proof but pattern. The stakes sharpen because strength, unlike composition, leans toward intent. A high area-to-mass object like Oumuamua invites the sail hypothesis. A high-strength, compact body invites the shield hypothesis, something designed to endure. If you were building interstellar hardware, you protect vulnerable components with material that doesn't shred at first touch with air. A hypersonic heat shield in miniature. That's speculation, but it's the kind that flows directly from a number on a graph. Skeptics pushed back on the narrative momentum. They cited populations of hypervelocity meteors in 2D datasets that also show deep fragmentation, objects likely metallic but natural. They warned that selecting the strongest-looking case and calling it unprecedented is how you fall for selection bias. They also noted that the spherule hardness distribution overlaps with known cosmic spherules from Antarctic collections and deep-sea surveys. The tales differ, but not in a way that demands industry, much less extraterrestrial industry. The reply was a bet on replication. If IM1 was natural and strong, we should find other interstellar meteors with similar deep breakup signatures and similar spherule fields. If it's engineered, we might see a bimodality, a class of bodies with strengths and microstructures that cluster away from known meteoritic families. Loeb proposed a simple scoreboard: map more fireball corridors, sample with standardized protocols, and publish the full distributions: hardness, composition, isotopes. Let patterns, not headlines, decide. Meanwhile, one detail kept needling the team. A subset of beads showed microstructures, fine dendrites and low porosity, consistent with rapid quenching from very high temperatures in a dense flow. That's compatible with hypersonic entry of metal, whether natural iron or alloy. But a few also carried trace element ratios odd for slag and uncommon in cataloged cosmic spherules. Those samples went into the queue for high-precision isotope work, where the interpretation gets less poetic and more binary. For now, strength sits at the center of the story because it's the thing that refused to budge under different readings of the curve. Even with generous uncertainties, IM1 looked tougher than it should be for its class. If engineered, it's the first artifact we've touched. If natural, it's a rare messenger from the metallic heart of a shattered world. Either way, it raised the bar for the next explanation and pushed Oumuamua's lingering questions back into focus. The great Oumuamua argument. By the time Oumuamua cleared the inner solar system, the instruments had already set the lines of battle. Spitzer stared and came up empty on warm dust, setting strict limits on the amount of fine material that could have been dragged off by venting ices. ALMA tuned to frequencies where carbon monoxide and carbon dioxide should sing if they were outgassing in any sensible quantity, and heard silence within its sensitivity. The lack of a visible coma wasn't just an aesthetic detail. It became a constraint box everyone had to live inside. Non-gravitational acceleration, though, wouldn't let go. The astrometry, multiple nights, multiple observatories, showed a residual push that fell off with distance from the sun, much like the 1/R2 dependence you'd expect from sunlight. If outgassing did it, you'd usually see some telltale: a torque on the spin state, a color change, a detectable trace of light molecules. People ran the numbers. To produce the observed acceleration with CO or CO2 jets given Spitzer's non-detections, the jets would need to be oddly efficient or tightly collimated, and the dust unusually sparse. Possible? Maybe. Typical? No. That's where the menagerie of natural models multiplied. The hydrogen iceberg camp argued that H2 sublimates invisibly and rapidly, generating thrust without betraying itself. Critics came back with thermal cracking math. Interstellar radiation and grain collisions erode H2 over long voyages. By the time such an iceberg reached the inner solar system, it should have been a ghost. The nitrogen shard hypothesis leaned on Pluto-like bodies. Impact ejecta could create slivers of N2 ice that later outgas quietly. But the production rate needed to seed the galaxy with enough shards to explain Oumuamua strain plausibility. Meanwhile, the fractal dust aggregate proposal painted a featherweight lattice with vanishing density, happy to ride photon pressure, yet somehow cohesive enough to survive perihelion heating. That solved the acceleration elegance, but asked for mechanical miracles. Loeb kept threading the same needle. If radiation pressure fits the acceleration cleanly and the object's effective area-to-mass ratio has to be high, then a thin geometry solves the math without contortions. Technology, as in a light sail or a solar-boosted sheet, becomes a reasonable, not dominant, hypothesis. He didn't insist on intent. He insisted on parity, that engineered options be allowed on the menu when natural options were already exotic. The pushback wasn't just scientific, it was procedural. Several teams reinterpreted the acceleration in terms of CO2 sublimation with updated thermal models, arguing that the non-detections didn't rule out a carefully distributed, dust-poor gas release. A 2023 paper suggested that trapped CO2 within a porous matrix could vent with little dust and still give the observed kick. Loeb's rebuttal was blunt. The model added knobs, thermal conductivity choices, poor geometries, jet collimation, that seemed tuned to make the outgassing invisible just enough to survive the constraints. He pointed to angular momentum budgets. If jets did the pushing, why didn't we see a commensurate torque in the light curve evolution? Meanwhile, other researchers explored the fractal route seriously. Could an aggregate with a fractal dimension around 2 have the right cross-section and low mass to feel photon pressure, yet retain enough strength? Lab analogs and meteor collections hinted that extremely porous cosmic dust exists, but scaling that up to hundreds of meters without collapse under self-gravity or thermal stress was a leap. Again, maybe did heavy lifting. Publicly, the narrative forked in two short phrases. One side said mundane comet with unusual properties. The other said technology candidate with simple physics. The word mundane did a lot of rhetorical work, downplaying how contorted some natural models became. Technology candidate, on the other hand, triggered institutional reflexes. It sounded like a verdict rather than a placeholder, even when framed as a hypothesis. A detail many missed sat in the data cadence. Oumuamua's brightness variations suggested a complex rotation state, possibly tumbling. Outgassing from an irregular body in a tumbling state tends to create time-variable thrust vectors and measurable changes in spin, which didn't cleanly appear. Radiation pressure, by contrast, acts consistently on whatever orientation presents the most area, nudging without needing jets to align just so. That didn't close the case, but it kept the light sail math tidy. The cultural memory of past false alarms hovered over every seminar. The Martian meteorite debates, the Viking biology experiments ambiguous signals, even the Allen telescope arrays false positive in 2015. Reviewers tightened standards in response, which is healthy science, but standards can freeze when data is sparse. With Oumuamua, the snapshot was all we'd ever have. That scarcity favored models you could bend to fit the holes, and punished any suggestion that pointed outside the usual playbook. Loeb's move was to shift from inference to acquisition. He argued that theory space could stretch forever without snapping. What would end the Oumuamua Trench War wasn't another thermal model. It was a repeated phenomenon you could touch. That's why he kept tying Oumuamua to IM1 in talks, not as proof, but as a strategy. One offers a dynamics puzzle, the other offers material. If they rhyme, you test the rhyme with isotopes, microstructures, and distributions, not adjectives. In the end, the great argument distilled to appetite for risk. Accept a natural explanation stitched from narrow corridors of parameter space, or allow an engineered hypothesis with fewer parameters but heavier implications to stand as co-equal, until a lab test knocks it down. The field mostly chose caution. Loeb chose to go find something that didn't care who was comfortable. The Galileo Project's gamble. Loeb knew talk wouldn't move the needle. Instruments would. The Galileo Project started as a simple promise: build systems that record unusual phenomena with enough fidelity that arguments shift from stories to statistics. He wrote the charter in plain language: search for unidentified aerial phenomena, track interstellar objects, and look for signatures of technology in space and on the seafloor. Then stapled two guardrails to it: open hardware, open data. On a rooftop in Cambridge, the first Galileo observatory looked nothing like a monolith. It was a stack of off-the-shelf sensors wired into a disciplined brain, wide-field optical cameras for day and night, thermal imagers tuned to spot heat plumes, radar feeds where available, and audio sensors to flag sonic booms. Everything time-synced to GPS, everything buffered locally and pushed to cloud storage, everything labeled so a grad student could trace a pixel back to a minute, and a lens with a known point spread. The ambition wasn't to outgun NASA. It was to avoid the photo of a light-in-the-sky trap that poisons discourse. Critics rolled their eyes. UAP research attracts noise, hoaxes, misidentifications, conspiracy theories. Loeb's answer was process. Each site would run calibrated cameras with overlapping fields of view, triangulating altitude and speed. Every detection would be cross-checked against catalogs of planes, satellites, and known atmospheric phenomena. False positives were the enemy. The pipeline would learn to swat them. The payoff wasn't a viral clip. It was a dataset any skeptic could audit. Money made the next choice for him. Traditional grants shy away from words like UFO in their abstracts. Panels don't want to defend them at budget hearings. Loeb went to private donors, some drawn by the romance of first contact, others by the thrill of science slipping past bureaucratic inertia. That brought its own skepticism. Was he chasing attention? He answered with contracts. Donors had no editorial control, and all data would be public on fixed schedules. If the project failed, it would fail in the open. The IM-1 expedition forced the project to grow up fast. Building a sky observatory is one challenge. Building a seafloor sampling program is another. Loeb hired engineers to refine the magnet sled, commissioned contamination studies in advance, and set up a lab pipeline that moved beads from jar to microscope to mass spectrometer with barcodes and logs. He reached out to oceanographers who'd mapped micrometeor spherules for decades and asked them to tear the plan apart. Some did gently, others declined, wary of association. The team hardened protocols anyway: blank toes, control transects, blind splits sent to independent labs. Inside universities, the reputational calculus hummed. Senior scientists whispered that curiosity was good. Press releases about aliens were not. Younger researchers weighed the risk of being labeled fringe against the chance to publish methods that could standardize a messy field. Loeb sat with both realities and made a bet. If you show your work at every step, hardware specs, calibration files, code repositories, the conversation has to live on the substance, not the label. The data platform was the project's spine. They built ingestion scripts that stamped every frame with star field solutions for night sky calibration and sun position for daytime glare modeling. The classification system flagged birds, drones, planes, meteors, and satellites with probability scores, and routed the tiny remainder to human review. They published the false positive rates like a scoreboard, inviting others to train adversarial models against their classifiers. Meanwhile, for Spherules, they posted elemental spectra and micrographs alongside the sample's chain of custody, daring critics to spot contamination holes. Skeptics still found angles. Funding through private gifts can pull projects towards spectacle. Loeb leaned into the boring, multi-sensor redundancy, pre-registered analysis plans, and commitments to release negative results. He called it the anti-UFO show. No dramatic teasers, no shadowy silhouettes, just raw feeds and timelines. The community didn't suddenly embrace him, but a few fence-sitters admitted the method looked like science, not theater. The project's gamble wasn't just hardware, it was scope. By linking UAP observations with interstellar object studies and seafloor searches, Loeb risked being accused of conflation. His rationale was strategic. If your goal is to find technology that didn't originate here, you should chase every channel where it could appear, bright in the air, faint in the sky, or cooled into beads on the ocean floor, and tie them with common standards that let you compare signal to noise. That way, a claim in one domain can be weighed against baselines in another. Momentum brought invitations Loeb didn't expect. A small observatory group in Europe asked to mirror the setup and pledged to share data. A Meteor network in Australia offered to cross-check Galileo detections against their Fireball cameras. Even a few critics offered to serve as external auditors, reviewing code and sampling plans under their own names. The project's value wasn't in a headline, it was in creating a path for replication. Still, the fight never left the peer-reviewed trenches. Papers submitted from the Galileo pipeline went through long rounds of revision, some rejected for scope, others for interpretation. Reviewers asked for more controls, more blanks, more humility in the abstract. Loeb took the notes he agreed with and published the ones he didn't on his blog, where the public read them faster than journals could reply. The bet remained simple: move from anecdotes to datasets. If nothing anomalous appears, that's a result. If something stubborn survives the filters, an object that moves without propulsion signatures, a bead with isotopes out of terrestrial range, it becomes a problem the community has to solve, not a story it can ignore. Data is messy, and reputations are brittle. The Galileo Project chose to live with both. Lab benches, mass specs, and accusations. The jars from the Bismarck Sea arrived with the weight of expectation and salt. In Cambridge and at partner labs, the workflow started quiet. Vacuum ovens to dry sediments, sieves to sort grain sizes, magnets to pull out the ferromagnetic fraction. Under scanning electron microscopes, technicians tagged textures, smooth skins, dendritic quench patterns, occasional splash tails. Then the EDS spectra rolled in. Iron dominating, nickel in the low single digits, traces of magnesium, silicon, chromium, manganese. Routine, until a subset refused to behave like routine. They logged internal IDs and pushed those outliers to the next tier. Inductively coupled plasma mass spectrometry. ICP-MS is where romance goes to die and science begins to argue. The nickel-to-iron ratios on some beads sat higher than typical industrial fly ash baselines published in environmental surveys, and a few carried trace beryllium and rare earth signals that didn't map neatly onto common slag fingerprints. Not alien, not even close, just interesting enough to circle in red. Loeb's team pre-registered their analysis plan, defined thresholds before conclusions, publish blanks, share raw spectra. Isotopes were the real prizes. Oxygen isotopes, when measurable in spherules, separate terrestrial signatures from extraterrestrial ranges. Iron and nickel isotopes can, in principle, point to parent body processes, core formation, shock events, cosmogenic exposure. The team queued samples for multi-collector ICP-MS and secondary ion mass spectrometry where grain size allowed. The first runs came back frustrating. Many beads were too small or too metal-rich to yield clean oxygen. Some iron isotope measurements were smeared by contamination at the parts per million level. They logged it all anyway, including the nulls. The internet prefers triumphs. Laboratories generate caveats. Accusations landed faster than isotopes. A materials scientist posted that stainless steel abrasion from the sled could seed the very beads being trumpeted. Loeb's lab responded with a catalog of the hardware. Austenitic 316L stainless, known chromium and nickel percentages, controlled surface treatments. Blank toes, with the sled raised, magnets wrapped but untouched by seafloor, produced a contamination signature they could subtract. Control transects outside the fall ellipse showed lower counts of the hardest, brightest beads. They published chain of custody logs, GPS tracks, timestamps, barcode scans. Critics said the chain didn't run far enough back. Who packed the magnet sleeves? Under what conditions? With what gloves? Meanwhile, a blog popular with Meteor researchers argued the Spherules. Elemental ratios matched coal fly ash cataloged near shipping lanes. Loeb's group counterplotted those datasets against their own. Some of their outliers sat well off the fly ash clusters. Others overlapped, which they acknowledged. They added an independent lab's replication. Blind splits sent to a second facility reproduced the nickel anomalies within error on key samples. When a reviewer asked for lead and bismuth traces, industrial markers that often tag slag, they included them, showing several candidate beads with low levels inconsistent with typical slag profiles. A microstory slid into the spreadsheets. In one vial, a bead fractured during mounting, revealing a dense, fine-grained core and a thin oxidation rind. Under nanoindentation, the core resisted like hardened steel. Under SEM, it showed minimal porosity. Its trace elements were odd, enough chromium to raise eyebrows, not enough to scream surgical steel. The team flagged it for transmission electron microscopy to image microstructures, grain boundaries, potential phase separations, that could hint at cooling history. Was this a quench from hypersonic entry of a metal-rich parent, or a tiny industrial pellet born in a furnace? The images would come later. The accusations arrived now. Peer review turned into a trench war of edits. One journal requested tighter statistics on spatial clustering, bootstrap the transect yields, compute p-values against a null of uniform background, show the effect size with confidence intervals. They did, and the clustering stayed, modest but real. Another insisted on noble gas analysis. Helium and neon trapped in microbubbles can reveal cosmogenic histories distinct from Earth-born particles. The team added a plan to dissolve select beads and run noble gas mass spectrometry, knowing it would destroy the very samples people were arguing about. Trade-offs are unromantic. Loeb posted updates in long-form notes, point-by-point replies to criticisms. He admitted where the data were thin, pushed where the controls held, and kept repeating the same invitation. Replicate the search at independent sites tied to other fireballs, pre-register methods with critics as co-authors if they wanted, and let the chips fall. Some took him up on pieces. An Antarctic microspherule group offered to share baselines. A marine geology lab proposed standardized sled designs to reduce abrasion. Others stayed in the commentariat, convinced the project was advocacy dressed as analysis. Inside the lab, the 30-second rule wasn't a rule but a rhythm. Every half-minute, someone asked, "What would make us wrong?" They ran acid baths on magnet sleeves, tested rinse water blanks, tracked airborne particulates in the clean room. They found a paint fragment once, red with iron oxide, and binned the entire batch it could have touched. They lost a week and gained credibility. A graduate student wrote a methods paper outline whose abstract contained no nouns ending in alien. Meanwhile, a preprint appeared claiming the beads' compositions fell within the broad umbrella of cosmic spherules collected worldwide. Loeb's team overlaid their hardest subset and showed a tail outside common catalogs. The debate narrowed. Not are they extraterrestrial, many probably are, but are they from IM1? That's where statistics met storytelling. the corridor clustering, the deep breakup inference, the hardness distribution. Together they sketched a parent you could believe in without seeing. Separately, they were noise. Critics said you can't sum weak priors into certainty. Loeb agreed, then asked for more priors. While the labs argued, he opened the second front, a statistical framework weighing the odds that multiple anomalies across domains, trajectory, fragmentation depth, spherule hardness, arise from selection bias versus a distinct population. He promised to publish the code and datasets, invite adversarial teams to try to break the results, and pre-commit to thresholds for calling anything a technology candidate. Because if the word is ever used, it has to survive more than a news cycle. It has to survive a lab bench. How many anomalies make a pattern? Start with odds, not headlines. If you're weighing technology against exotic nature, the prior for alien hardware isn't generous. But priors aren't handcuffs, they're starting points. Loeb's pitch is Bayesian in practice. Update beliefs as independent clues stack: interstellar speed, deep breakup, clustered hard spherules. Each on its own is weak T. Together, do they tilt the scale enough to justify treating technology candidate as a working label rather than a taboo? First, know the catalogs you're leaning on. Do these sensors see a selective sky, bright, fast, sometimes small, optimized for threats, not meteors? Civilian fireball networks catch different animals, slower, bigger, often with better light curves but fewer at high speed. That's selection bias hiding in plain sight. If you notice a cluster of hypervelocity events in the 2D set, some could be instrument favor, not astrophysics. Loeb's answer isn't denial, it's calibration. Crossmatch 2D events with civilian detections where overlap exists, and simulate what each network would have seen given the same sky. If a pattern survives that translation, it's more than an artifact. He builds the frame like this. Define a null model where interstellar meteors are rare outliers drawn from a broad tale of natural strengths and compositions. Then ask how surprising the IM1 package is under that null. You fold in the Pentagon's velocity confidence as a likelihood term. You add the deep breakup inference with conservative luminous efficiencies. You weight the spherule clustering with bootstrap tests against uniform background. The output isn't a drumroll to aliens. It's a number that says, this bundle is X times likelier if there exists a distinct population with higher strength than if all meteors come from one distribution. Meanwhile, he widens the context to keep from cherry-picking. Oumuamua sets a data point for interstellar wanderers with odd dynamics. 2I/Borisov anchors the other pole, a textbook comet with a coma and outgassing, normal as cold dirt. Add the 2024 Atlas interstellar comet and similar findings, and you sketch normal for interstellar bodies, mostly cometary, volatile-rich, messy. Against that baseline, Oumuamua sits strange. IM1, if interstellar and strong, sits strange in a different quadrant. Two orthogonal anomalies don't make intent, but they dent the assumption that all interstellar visitors look like Borisov. Skeptics counter with survivorship bias. You remember the weird ones, forget the dull. A catalog heavy with routine comets creates no headlines. A single oddball spawns a cottage industry of papers and podcasts. Loeb's response is to pre-register blind hunts, define in advance what qualifies as anomalous, then scan the catalogs without peeking and see how many hits you get versus expectation. If the rate of high strength, deep breakup interstellar meteors is above what natural models predict, the prior shifts. If it isn't, the case deflates, and you post the negative. He also leans on the therefore chain instead of and then. IM1 looks interstellar, therefore sampling the corridor matters. The corridor shows clustering of hard spherules, therefore laboratory differentiation becomes the next gate. Labs find isotope baselines within cosmic ranges, therefore the tech hypothesis loses weight. Labs find out-of-family isotopes or microstructures inconsistent with slag and known cosmic spherules, therefore the weight increases. Each gate is a decision point that updates the odds, not a flourish in a story. Unknown to most viewers, A parallel statistics debate runs under the hood: hierarchical modeling versus single-event inference. If each fireball event carries its own uncertainties, and each laboratory measurement carries its own error bars, pooling them demands a model that respects those layers. Loeb's team writes code to share, promising priors that critics can swap and rerun. That's how you keep from smuggling conclusions in through the assumptions. While that was happening in code, he asked a blunter question: how many anomalies do you need before you change your search behavior? 1, 2, a handful in different domains. The cautious answer is more than we have. The pragmatic answer is enough to justify small, targeted bets. That's where he lives, designing intercept concepts for future interstellar objects, drafting trigger criteria for ocean searches, and setting public thresholds for the phrase technology candidate, so it can't be abused. The stakes aren't academic. A real pattern implies a real process. A process hints at origin. If the pattern is catalog bias, better instruments will erase it. If it's nature being inventive, we'll map a new class of interstellar metal-rich bodies. If it's technology, the next detection will be the moment the prior finally yields. And that's why his next move asks a different question. If it's tech, what's it for? If it's technology, what is it for? Start with the simplest jobs a thing can do in space. A sail can ride sunlight. A courier can carry bits. A shield can protect something fragile. If Oumuamua behaved like a high area-to-mass sheet and IM-1 looked compact, fast, and strong, you can sketch 2 roles on a napkin: scout and armor. Not because we want it, but because those roles drop straight out of physics. Radiation pressure favors thin films. Hypersonic survival favors tough metals. A light sail is the cleanest story. A wafer-thin sheet with low mass can feel photon pressure and steer with tiny torques. If it's passive, it needs no fuel, just geometry and time. A sail could be a derelict, debris from a failed mission, or a functioning reflector designed to skim star systems and phone home by bouncing modulated light. The constraints are brutal. Thermal limits near perihelion, micrometeoroid scars accumulating over millions of years, and the tendency for thin films to crumple or tear. Engineers counter with coatings that reflect broadly, microribs to hold shape, and sacrificial layers that accept punctures without ripping catastrophically. A courier is quieter. Think of a centimeter-scale probe that stores data in robust memory, encased in a heat-resistant shell. It doesn't need to slow down. It just needs to survive a pass through the inner system and broadcast a burst if it sees something interesting, or simply seed nodes that later civilizations might find. Power is the choke point. Solar at interstellar distances is meager. Options include long-lived radioisotopes, energy harvesting in a star flyby, or beamed power. Catch a pulse from a parent civilization's transmitter and convert it to electricity for a brief, intense window. Then there's debris. Not every artifact has intent left in it. A fragment of a larger probe, heat shield tile, radiator panel, structural cap, could drift as interstellar trash. If a heat shield tile fell off or a vehicle shed cladding under thermal stress, you'd expect compact, strong pieces with high melting points. A metal-rich object hurtling into our atmosphere, resisting breakup longer than usual, fits that profile. The spherules could be the slag of a failed entry. Engineered material, turned to droplets by a hypersonic plasma bath. Some ideas go bigger. Planet seeds, self-replicating machines, or biological packages require extraordinary complexity and ethics that make people flinch. But you can strip it back to mechanics. A capsule that can endure radiation for eons, survive a quick dunk in an ocean, and then do nothing more than persist, waiting for a detector. Engineering for that world looks like layered ceramics, alloy shells, and microstructures tuned to absorb shock. None of that violates physics. All of it strains credibility without evidence beyond a light curve and beads. Guidance is the unsung villain. A thin sail can surf gravity and light, but it needs control to hold course, maybe micromass shifts, electrostatic curvature, or tiny vanes. A compact shielded object needs aiming if it's supposed to hit something specific. Without active steering, you accept statistical sampling, spray enough units, and a few cross-habitable zones. That's ugly but scalable if your civilization's manufacturing is cheap over cosmic time. Power sources set ceilings. Solar is great near stars, terrible in the dark between them. Nuclear microbatteries can last decades to centuries, not millions of years, unless you park them dormant and wake on cue. Beamed energy, laser or microwave, lets you go light and fast, but the infrastructure screams active steering. That leaves passive artifacts as the conservative bet, things that work without asking much from time. Failure modes tell their own story. A sales edge phrase, radiation embrittles polymers, meteoroids pepper holes. A compact object accumulates microcracks, then shatters under thermal shock at first touch with air. If IM-1's parent truly stayed intact deep, it either avoided those cracks or was overbuilt for them. That could mean alloy choices that don't exist in nature, or just nature doing what it does in planetary cores. Forge iron-nickel phases tough enough to fool us. Ethics hangs over the speculation. If these are passive artifacts, they aren't watching us, they're drifting through, indifferent. If active even a little, you wonder about surveillance and consent. The sobering counterweight is scale. Our instruments barely noticed Oumuamua and only inferred IM-1 after the fact. If a civilization wanted to look closely, it would do better than this. That argues against the drama and for the mundane. Scouts that don't care who sees them, debris that doesn't know we're here. So what do you build if you're them? You build simple things that survive, thin things that feel light without leaking gas, tough things that don't shred at the first hint of air. You don't make them perfect, you make them many. Some will graze stars, some will skip off atmospheres, and a few will kiss an ocean and crumble into beads that an impatient astronomer will chase with magnets. This is where Loeb's restraint and provocation meet. He's not claiming to know the mission plan. He's arguing that the behavior we've measured, one object nudged like a sheep, another breaking like armor, matches roles that engineers on any world would recognize. And if NASA seems quiet here, he'll say that's not a conspiracy, it's culture. The agency lives on caution. He's betting that a clear function will announce itself only when we stop guessing and start catching the next one in the act. NASA's silent, science's guardrails. While the public waited for a trumpet blast, NASA mostly spoke in footnotes. Press officers used careful phrases, anomalous understudy consistent with natural explanations, because the agency has a long memory. Inside headquarters, there's a rule of thumb older than some missions. Avoid headlines that outpace data. It isn't fear of truth, it's survival. One sensational claim that collapses can cost a decade of political capital, which pays for telescopes and launches. Institutional conservatism didn't appear from nowhere. In the 1970s, Viking's life detection experiment on Mars returned mixed results. One instrument hinted at metabolism, others didn't. The argument scarred a generation. In 1996, a team announced possible microfossils in Martian meteorite ALH 84001. The president praised it on live TV. Years later, most of the community judged the evidence non-biological. Couriers survived, but the phrase extraordinary claims became a shield and a scar. Add the UFO stigma that hovered over public discourse for decades, and you get a reflex. Step gingerly, especially near the word alien. Funding politics reinforces the posture. NASA's budget rides annual appropriations that pass through committees allergic to controversy. Mission proposals are graded by panels that reward clear, incremental returns. A PI who inserts speculative language in a science plan risks reviews that say interesting but risky, which can sink a billion-dollar effort. So when Oumuamua's strangeness cracked headlines, and when IM-1's letter surfaced, NASA-affiliated scientists mostly stuck to conservative lanes. Publish constraints, propose better surveys, avoid intent. Data custody makes it harder. The DoD owns the best global sensors for bright meteors. Their calibration, timing, and spectral response live behind classification. NASA can relay generalities through the CNEOS database, but when error bars are locked away, program managers can't hang policy on them. You can't direct a rapid response mission with half a dataset. Even when Space Command releases confident statements, the pipeline from secret sensors to open science runs through review bottlenecks that take months or years. Inside rooms with closed doors, scientists debate like everyone else. Some argue that Loeb's pace risks outpacing proof and dragging the field into a media loop it can't control. Others say the opposite. Silence cedes the story to people who don't care about controls. The compromise shows up as process. NASA funds surveys, Vera Rubin collaborations, NEO surveyor development, because better detection reduces speculation. When you can see more, you guess less. Loeb's critique lands where culture meets curiosity. He says big science has become too risk-averse, optimizing for consensus and citation counts over bold tests. From his perspective, the guardrails have grown into walls. No one wants to be the person who writes technology candidate in a paper that might haunt their grant renewals. He contrasts that with the Galileo Project's open data stance. Show the raw, pre-register methods, invite critics in at the design stage. If you get it wrong, you get it wrong in public and science moves. NASA has countervailing responsibilities. The agency's credibility is a national asset. It carries the memory of Apollo, the Hubble fix, the Perseverance landing. When it speaks for more than a lab group. That pushes it toward the median interpretation, which for Oumuamua means likely natural with unusual properties. And for IM one means interesting but composition unknown. Internally, mission concepts for interstellar interceptors are floated, matured, and ranked without ever needing to say aliens. Because the engineering case stands on its own, any interstellar object is worth chasing. There's also simple bandwidth. Planetary defense offices track near-Earth objects. Astrophysics divisions shepherd missions with decade-long timelines. Heliophysics watches the sun. A small, controversial thread can't commandeer the whole loom. So NASA funds incremental upgrades, faster pipelines for orbit solutions, research into non-gravitational forces on small bodies, laboratory studies of spherules from known meteorite falls, without branding any of it as a referendum on ET. Past scars shape communications. After ALH 84001, internal guidance shifted towards stronger internal review of extraordinary claims before public statements. After decades of UFO ridicule, recent UAP taskings have been framed as air safety and sensor characterization, not as extraterrestrial inquiry. That framing lets engineers study weird data without inheriting the stigma. It also means the word alien won't appear in a NASA release, unless the evidence can bench press a mountain. Loeb pushes on the culture because he believes public curiosity is an engine, not a hazard. He argues that openness inoculates against overreach. If everyone can see the methods, hype dies on contact with details. He also knows the flip side. Overclaiming erodes future credibility. So he tries to thread it, put the bold hypothesis on the table, tag it as a hypothesis, and build tests that can kill it. Meanwhile, the public moved faster than journals. Media cycles turned anomalies into memes. Podcasts crowned Loeb a maverick or a showman, depending on the day. NASA's calm sounded like evasion to some, prudence to others. The truth is duller and sturdier. Guardrails keep the car on the road while people argue about the destination. The next object, the next dataset, will decide who gets to grab the wheel. Media, memes, and the court of public opinion. The labs were still pipetting when the headlines arrived. Harvard professor finds alien metal in the Pacific. It's not what the papers said, but it's what the thumbnails wrote. On YouTube and TikTok, the story collapsed into a meme. Loeb as the brave truth-teller, NASA as the stodgy gatekeeper, and a handful of shiny beads cast as the smoking gun. Nuance doesn't go viral, characters do. Loeb became a character whether he wanted it or not. Maverick to some, self-promoter to others. Clips of him calmly explaining dynamic pressure and isotopes got chopped into 10-second sound bites that sounded like declarations. Meanwhile, his critics' careful caveats, contamination, error bars, priors, were edited into eye rolls. The algorithm rewards certainty. Science trades in degrees of confidence. Those two economies don't clear at the same price. A micro-story caught the mismatch. In a radio interview, a host asked Loeb, "So, aliens," he said, "we don't know yet, we need isotopes and replication." The show's social post read, "Harvard prof, alien tech possible." Both statements were technically true, only one traveled. NASA's brand lived on the other side of the glass. To the public, it's the grown-up in the room, Hubble pictures and Mars rovers, the voice you trust not to oversell. That trust cuts both ways. When NASA-affiliated scientists leaned toward natural explanations for Oumuamua and stressed uncertainty for IM-1, fans of the agency heard prudence, fans of the chase heard hedging. The same sentence, interesting, likely natural, more data needed, landed as stability to one crowd and stonewalling to another. Memes filled the gap. A looping clip of Loeb holding a spherule became reaction fodder. When NASA says it's a rock, threads argued over nickel ratios like sports scores. A skeptic's blog post would spike, then a rebuttal on Medium would counter, both read more widely than the peer-reviewed papers they referenced. In that court, speed beats rigor. By the time a journal publishes a methods section, the meme has moved on. Loeb fed and fought the cycle. He posted long-form notes with plots and protocols, invited critics to replicate and showed his receipts, calibration files, chain of custody logs. He also wrote with heat when he felt models were tuned to fit conclusions, and heat gets quoted. Supporters clipped the sharp lines. Detractors clipped them too, as evidence of advocacy. Somewhere in the middle sat the work, sled tracks on the Bismarck seafloor and spectra that didn't care about hashtags. The audience's hunger shaped the battlefield. Contact stories pull clicks because they tug at belonging and scale. Are we alone? And if not, who are we? That attention is pressure. Journal editors know it, program managers know it. It can pry open doors for unconventional proposals, and it can slam them shut if a claim collapses loudly. A single overreach in public can shadow an entire subfield for years. People who remember ALH 84001 learned that lesson by attrition. Meanwhile, science communication tried to thread the needle. Some outlets hosted debates where both sides spoke past each other. Engineers asking for testable predictions, astronomers asking for conservative priors, and hosts asking for a headline. A few shows got it right, walked through the light curve, asked what would falsify the tech hypothesis, pressed NASA voices on how quiet is too quiet. Those episodes did modest numbers. The ones with alien in the title did not. Trust became the currency. NASA's institutional trust is thick, decades of deliverables. Loeb's personal trust rests on transparency, show the data, take the hits, keep going. Viewers sort themselves by which trust they prefer, the brand that rarely speculates or the person who says the quiet part out loud and invites you into the kitchen. Neither approach is wrong. Both can be gained. Grifters wear lab coats online. Bureaucrats can hide behind caution. The antidote to both is method, published in daylight. Backfire risk lurked in every thumbnail. If a bead hailed as anomalous turned out to be ship paint, the correction would crawl while the original claim sprinted. If NASA waited too long to engage, a vacuum would fill with conspiracy theories. The middle path looked unglamorous. Pre-register searches, publish negative results, and let the audience see the sausage made. That isn't a rating strategy. It's a credibility strategy. By late summer, the noise swelled enough that Loeb's team issued a plain pledge. No technology language without multiple independent lines. Spatial clustering, isotopes outside terrestrial ranges, microstructures incompatible with slag, and replication at another event site. It read like a truce flag to peer reviewers and a buzzkill to fans, but it planted a marker the memes couldn't move. Strip the noise and you're left with the real question. What do we actually know? And what's the next test that could change it? What's solid, what's speculative? Let's pin down the ground we can actually stand on before we argue about what's on the horizon. First, IM-1's origin. The U.S. Space Command's 2022 statement, based on a classified reanalysis of timing and calibration, put the meteor's pre-atmospheric speed solidly above solar escape with 99.999% confidence. That's not a press quote. It's an internal validation that the hyperbolic solution survives realistic error bars. We can treat IM-1 as interstellar in origin with high confidence. That's solid. Next, Oumuamua's behavior. Multiple nights of astrometry showed a small but persistent non-gravitational acceleration that decayed with distance like sunlight, and yet telescopes sensitive to dust and common volatiles returned non-detections. Spitzer's constraints on warm dust and ALMA's limits on CO2 mean if outgassing occurred, it had to be dust-poor, oddly efficient, or otherwise atypical. That's not conjecture. Those are published upper limits and a measured trajectory. Also solid. Now the beads. Metallic spherules fall from the sky all the time. Cosmic dust and industrial byproducts both make them, so their mere existence proves nothing. What's likely is that a non-trivial fraction of the collected spherules are extraterrestrial micrometeoric material, because their textures and bulk iron-nickel compositions match known cosmic spherule classes. Some subset in the IM-1 corridor appeared harder and more compact than average, and their counts were higher along transects mapped to the predicted fall ellipse than along controls. That clustering is evidence, not confirmation. Likely, but not decisive. What remains unknown decisively is intent. We do not have engineered composition in hand. We don't have microstructures that unambiguously require human-like metallurgy, precise alloying ratios outside natural ranges, layered architectures, or manufacturable grains. The 2D light curve implies unusual strength if interpreted with conservative luminous efficiencies, but strength alone doesn't prove manufacture. Iron meteorites and shock-hardened phases exist in nature. Unknown until better constraints narrow those paths. Oumuamua's cause is also still open. A thin, high-area-to-mass structure pushed by radiation pressure fits the acceleration elegantly, but implies fragile geometry rare in nature. On the other hand, updated thermal models argue volatile release could push without violating the non-detections if the jets were dust-poor and distributed just so. Both lanes survive because the data are sparse. Unknown, with live hypotheses on both sides. So what would move pieces from unknown to known? Isotopes first. Oxygen isotopes in silicates, when measurable, put spherules on or off terrestrial fractionation lines. Iron and nickel isotope ratios can point to core formation processes and cosmic ray exposure histories that differ between industrial slag and meteoritic metal. Noble gases next. Helium and neon trapped in microbubbles or dissolved in metal can record cosmogenic irradiation, a fingerprint hard to fake and easy to misread if contamination intrudes. Microstructure matters too. Transmission electron microscopy that shows quench textures, grain sizes, and phase distributions that either mirror known cosmic spherules or look engineered. Then there's replication. Sample other fireball corridors that share IM-1-like signatures, hypervelocity, deep breakup, and run the same sled, the same clean protocols, the same blind splits, preferably by independent teams. If the same hardness tail and trace element patterns recur along predicted center lines and nowhere else, the statistical weight grows. If they don't, we learn that the IM-1 site was ordinary dressed up by chance. For Oumuamua, the tests come from the sky. The Vera Rubin Observatory will flood us with light curves for small visitors, including interstellar ones. If many show similar non-gravitational accelerations with weak coma signatures, the weird becomes a class, and models must scale. A dedicated rapid response mission, small interceptors that can reach an incoming object within months, would rewrite the arguments. Close imaging beats creative models. Even a flyby that measures outgassing directly or maps shape precisely would collapse the parameter space. That's testable with planned concepts. Speculation belongs where physics opens doors and evidence hasn't walked through yet. A light sail explains a clean 1/R2 push. A compact, high-strength body hints at shielding. Those are roles, not verdicts. They should be treated like any hypothesis. Publish the criteria that would falsify them, set thresholds ahead of time, and accept the hit if the data land elsewhere. Until we see alloying outside natural ranges, until isotopes say, not slag, not ordinary meteor, until replication pins down the spatial signal, technology is a candidate word, not a conclusion. Here's the sober ledger. Solid. Oumuamua's interstellar origin, Oumuamua's non-gravitational acceleration and lack of standard outgassing signatures, the existence of a clustered hard spherule subset along a mapped corridor. Likely, a portion of the collected beads are extraterrestrial. The hardness distribution suggests a tough parent, though not uniquely. Unknown, whether any material is engineered, whether Oumuamua was a sail-like object or an odd, volatile poor visitor, whether Oumuamua's parent was natural iron or something built. The next moves are unglamorous and decisive. Isotopes with posted blanks, noble gases with destructive honesty, microstructures at nanoscales, replication across oceans, and sky surveys that catch the next one early enough to meet it face to face. The argument won't end on a blog. It'll end when those numbers arrive. The next shot from the stars. The next decision won't be made on a blog. It'll be made by telescopes that don't blink. The Vera Rubin Observatory is about to turn the sky into a movie, scanning the entire visible dome every few nights with the LSSD pipeline catching movers fast. That means more interstellar interlopers flagged early, not months after the fact. Pair that with Atlas and Pan-SDARRS upgrades, and you get notice. Not perfect, but enough to plan an intercept instead of writing obituaries for missed chances. NEO Surveyor adds another lens. It looks in infrared, where cold bodies betray themselves, and that helps separate rocks from fluff, comets from something stranger. Together, these surveys build a trigger. When an object shows hyperbolic motion and odd brightness behavior, you don't debate on Twitter, you cue a rapid response. Small interceptors, even CubeSat-class chasers with solid boosters, can ride shared launches and wait in parking orbits. Give them modular instruments. Imaging, a simple mass spectrometer for outgassing, a laser altimeter for shape. If one's lucky, a dust analyzer to sniff any particles. The concept isn't sci-fi. Space agencies already study comet interceptor architectures, park a craft at L2, sprint when an interesting target appears. Scale that down, run it twice a decade, and you change the Oumuamua problem from we don't know to we went and saw. Even a fast flyby at a few kilometers per second would settle key questions. Is there a coma? What's the shape? How does it tumble? Does sunlight push it the way a sail would? A close pass replaces 1,000 models. On Earth, ocean searches need to standardize or stop pretending they can persuade skeptics. That means a playbook, pre-registered drift models published before sailing, sled designs with abrasion tested and reported, blank toes logged, control transects defined in advance, and chain of custody software everyone can see. Add sediment cores to date layers. Use radionuclides like 210 pb to pin the year of deposition. If a corridor spike sits at the right depth, the argument gets teeth. If it doesn't, you publish the null and update priors. Open data is the glue. Build coalitions where meteor networks, naval oceanographers, and lab geochemists share formats and timelines. Pre-commit to releasing raw spectra, calibration files, and code. Invite adversarial collaborations, critics as co-authors who sign off on methods before sampling. That sounds idealistic, but it's how you survive an extraordinary claims environment without burning trust. Decision points need clarity. Define thresholds for calling an object a technology candidate, so the label doesn't rot. For sky targets, Sustained non-gravitational acceleration consistent with radiation pressure, no detectable volatiles within instrument limits, and shape orientation that yields a high area-to-mass ratio. For meteors, interstellar origin validated by independent timing networks, fragmentation depth implying strengths above known meteoritic distributions, spatially clustered spherules with isotopes outside terrestrial and typical cosmic ranges, and replication at a second event. Miss one gate, downgrade the claim. Hit all, escalate scrutiny. Meanwhile, engineering groups should prototype capture, not just chase. A small aerogel collector deployed in the upper atmosphere during a predicted stream could snag microdebris from an incoming interstellar meteor. Balloons at 30 kilometers with magnetic collectors might catch molten droplets mid-fall, preserving gases and surfaces ocean water would erase. It's messy, but cheaper than ships and cleaner for contamination. Rubin's deluge will also teach humility. We'll see hundreds of weird, light curves that resolve into mundane rotations once sampling improves. That's good news. Anomalies that survive that tide are the ones worth burning fuel on. The point isn't to make alien headlines. It's to prune false positives until what remains demands new categories or new narratives. What nobody says aloud often enough is cost. A rapid response interceptor program could live for the price of a mid-scale astrophysics mission if designed lean. A few spacecraft on the shelf, rideshare launches, a standing ops team. Ocean campaigns can be federated across nations, sharing ships and labs. The payoff is asymmetrical. One clean flyby of a strange interstellar object, one bead with isotopes that won't fit, and decades of speculation either stand taller or sit down. It comes down to appetite. Build systems that assume the next outlier is coming, or keep arguing in the gaps between surveys and secrecy. Loeb's wager is simple. Be ready to move when the alert pings, and set the rules before the excitement hits. Because the next shot from the stars won't wait for a committee. Resolution plus broader meaning. Curiosity outruns consensus, and anomalies force the map to expand whether we like it or not. If these are artifacts, we've been noticed. If they're natural, nature's toolkit is wilder than our models. Don't just watch, be here when the alert pings. Tap subscribe, share this with the one friend who will argue back, and cue our rapid response interceptors deep dive. The moment the sky throws another rock, we move.